All right. Well, I'm really pleased to kind of kick off this first presentation and tell you more about a project that we are all part of. So this is the Neuro Cybersecurity Project. It is an NSF-funded project through Smart and Connected Communities. And this is actually our second presentation on the topic. We hosted a virtual panel back in December, and we're just kind of continuing to build and share on what we're doing. So the lineup for today is you're going to first hear from me, and I will be talking about community engagement research, and this is led by the University of Illinois Urbana-Champaign portion of the team. Then we're going to hear from the clinical research team, both Dr. Erika Petersen and Dr. Julian Goldman, to share their perspectives from kind of the clinical perspective. And then we're going to hear from Wayne Burleson, who's kind of representing the hardware security research team. So that's where we'll start our journey today. So starting off, I'm talking about perceptions in security and privacy related to neural implants. And like Kevin just mentioned, neural implants kind of span these two categories. So I know not everyone here is from a neural kind of context. So just briefly, when we talk about a brain-computer interface, we're talking about something that is integrated into the brain and maybe reads signals from the brain and allows the user to complete some sort of function, either to control a physical object, a virtual object, to kind of help their daily life. So people who have maybe lost function of limbs can then become more autonomous and independent. On the other side of that, we have neural stimulators. And like Kevin mentioned, those could be chemical, so drug delivery, could be mechanical, like vibration sensation, or it could be electrical stimulation. So there's lots of different stimulators and not just limited to the brain, right? Neural stimulators can be implanted anywhere in the body to stimulate nerves as needed for that type of patient care. So I wanted to start to kind of orient everyone to a little bit of a case study that I put together. And so this case study focuses on our patient Marcus, who's pictured here, who is living with quadriplegia. And so he has some limited mobility of his arms and is able to use a powered wheelchair, but really needed some assistance in terms of interacting with a computer. And so here he is seen controlling a digital cursor, and he also has a robotic arm that he uses for feeding that he can control as well. So in this case study, we start off with kind of the honeymoon phase. Marcus experiences kind of this embodiment of this connection he feels with his digital cursor. He feels like it's an extension of his own body, which is really what a lot of users report. Then he kind of goes through an identity crisis. Marcus notices that the AI seems to autocomplete his thoughts. He starts thinking about a folder, and then suddenly the cursor clicks to that folder, and he thinks, did I do that? Or did the AI anticipate that this is what I wanted? Am I really in control of this cursor? Then he starts to have a realization that if there's a lag in the system, that he is completely dependent on this technology to complete some of his tasks. And he starts to feel a little almost like digital claustrophobia, like really tied in to this device to complete his daily functions. So I share this patient story with you to kind of orient you to, what patients perceive when they're using these devices and how important it is to think about the patient perspectives. And it comes down to this autonomy paradox. So patients really strive to regain some sense of normalcy and autonomy and independence. That's why they usually choose to receive some of these different neural stimulators or brain-computer interfaces. But at the other side, there's this idea of, am I really in control of it? Or is it kind of in control of me? And then who am I if I am not in control of this device? Is it really me? This is something that a lot of users convey when they are experiencing these different neural technologies. So again, what do we hear from patients? This is based on a conglomeration of review papers that have looked into patient experiences, that, like I said, they experience and why they want the devices for independence and autonomy, to reduce reliance on others and caregivers, and just feel like they have more control. But of course, there's lots of challenges. And so, many of our users have setup complexity issues. They have concerns about reliability and longevity of their devices. And of course, the devices need some sort of regular maintenance or upgrades. And how do they keep up and make sure that they're always up to date on the latest technology that's available for their device? Of course, there's also some psychological and social impacts. So, how does that use of an implant change my perception of my identity and who I am? And also, there's stigma and social perception. If I'm using some sort of a brain-computer interface or a controlled device, am I somehow superhuman, or am I going to be judged or feel like an other because of that device? So when we're talking about specific threats, there's a lot of concern about like mental privacy. So could these devices kind of be thinking about subconscious cues, kind of like I think about the folder and the cursor moves, but I didn't try to intentionally move the cursor? Or private thought. So if we can read someone's brainwaves and figure out what song they're listening to, certainly we can read someone's brainwaves and try to figure out what they're thinking about. And that's a pretty invasive a way to think about people understanding your inner dialogue, right? Your most personal moments. And then our last seminar in December really focused on this idea of brain jacking. And so could a bad actor do signal manipulation or extract data from these types of devices that then, again, really invades someone's privacy or changes the way that maybe they are because of this control issue? And so there's a lot of, technological and hardware-based issues that are going to come up later in this session. So I put together this little table just to kind of get people started to think about connecting design solutions to patient concerns. So a patient concern might be, is this me? Am I really in control of this? And am I acting in a way that I want to act? And so the psychological risk to that is personal agency. So what can we do on the design side as, device designers? Make sure that the patient always has kind of like the final say or the final veto with what the device is going to do. This idea of who's listening, who has access to my thoughts, it's an invasion of mental privacy. And so we want to make sure that, if we're reading raw data, that we never are interrupting or trying to manipulate neural data that's coming in real time. And what if it breaks? This is always a concern that we have. What's the longevity? What's the life of this implant or device even? Is it going to be supported for as long as I need to use it? And so we want to make sure that, if a device is going to fail, that it fails in some sort of a safe mode. So what is the default safe mode for the device? And that may vary device to device in terms of what we need to think about when designing these types of devices. So kind of to close out my kind of patient-focused side, in neural design, a bug isn't just a software failure. It could be a complete violation of a user's sense of self. And so, we have to think about this in a slightly different way where we respect the autonomy and kind of psychological impacts that these devices have on people in a way that maybe we wouldn't with other types of stimulators elsewhere in the body. And so with that, I'm going to pass off to Erika, and Erika, just let me know when to advance the slides.
Thank you, Dr. Amos, for that wonderful update on things. And I think it's such an interesting time for these devices because it's really in the past 20 years. Some of these devices were developed first 40 or 50 years ago, but with the amount of technological advances that have developed and the number of applications that have proliferated, we are starting to see more and more patients who have access. And just in the past 5 years, the brain-computer interfaces are coming into their own, although still really in clinical trials, not in full commercialization. So it's not science fiction anymore. This isn't an episode of The Twilight Zone, and a lot of the questions that you highlighted come into things that used to be on The Twilight Zone or Black Mirror, or one of those things instead. And so privacy and security are really an important part of that. And it's very obvious that we as clinicians have not had the opportunity to provide the education, the ethical and social context that goes with grappling with how this changes our culture and changes our patient experience. And so it is really an interesting nexus that we're going to be able to experience all these things. If you could go to our next slide, please, Jenny. So the risks and vulnerabilities, you heard some of these. These are things that we've seen published just in terms of denial of service attacks, unauthorized data access, unauthorized control of device, the interruptions of device function, and then the misappropriation of data. This is something that, again, you've heard Jenny touch on these issues from the patient point of view, but these also then impact what we're able to deliver as clinicians caring for individual patients, and also as we think about how we build the clinical systems that manage healthcare and outcomes for large groups of patients. If we cannot have access to data and the systems that support those data, then we have patients who are marooned with the technology that's not able to support them. If we have a patient whose data were uploaded and recorded 5 years ago, and now there is an upgrade to the system and the technology and an advancement in the AI paradigm, for example, that's analyzing those data, we can get insights from historical data that potentially were not things that the patient initially agreed to have accessed. And how does that patient then navigate this new update to things? And so these are really important piece of it. I might agree that my data about how I go on a run with Strava is valuable to me for health and fitness points of view. But when the Strava run maps get published in the Washington Post showing the outlines of military bases, as was done about 5 years ago, then we find that there's misappropriation of that data being used for a totally, completely new insight that is not from the intended purpose and the design of that application. So we took this information and these concerns and wanted to sort of take a temperature on the clinical environment of surgeons and people who managed neuromodulation devices. And I want to show you a little bit of what we got from the results of that survey. Next slide, please. So this was an online survey that we posted across multiple social media platforms in order to try to sound what people who use neuromodulation, that would be neurosurgeons, neurologists, interventional pain physicians, physiatrists, and ask them, first of all, how familiar were these people with issues in device cybersecurity? And we stratified this by the number of years that people were in training, including those who are residents and fellows, that would be 4 years out of medical school, to those who are seasoned veterans. And you can see that very few people say that they're very familiar. Really about half of people report to have no familiarity at all with issues of device cybersecurity. These are clinicians who are prescribing or implanting these devices and using and recommending these to patients who don't know about cybersecurity issues of the devices that they're choosing to utilize for those patients. And then we asked them how would they rate their knowledge compared to the rest of their perception of how the rest of the field is doing. Everybody thinks they're about average with the rest of the field. Nobody says they're below average. But the general gestalt being that these topics don't come up in the conversations among clinicians that happen at academic conferences or in sharing of information and decision making, and the ways that people are learning about how to apply these technologies into their practice. You look at this at the next level, and we'll take the next slide, please, for that. What about data privacy? Again, you see that some people think that they have some familiarity or somewhat familiarity. It's definitely a smaller group who say they're not familiar compared to device cybersecurity. And I would suggest that a lot of this comes from the fact that the issues of data privacy that come from general data privacy or financial data privacy that we encounter just as commercial consumers is something that translates into understanding of data privacy within the medical environment. However, it doesn't have the nuance to some of the medical privacy piece of it, and only has some overlap with what we know about HIPAA privacies for medical information, for example. Next slide, please. Finally, we asked, do you talk to your patients about device cybersecurity? And you can see that only one sliver of one senior person said that they always talk to patients about cybersecurity when they're having conversations about these devices. And a large portion of people never talk to their patients about privacy and cybersecurity. What that really reveals, again, is that when people are unacquainted with the issues, uncomfortable with the issues, of course you don't bring up that topic, you're not an expert expert in it or have the authority to share that or even know where to start that conversation. So there's a real opportunity for a project like ours to bring a context of why these are hot button issues, to have an easy starter kit of how to understand these issues and how to have these conversations in a way that makes us approachable and understandable within the clinical environment for clinicians, for implanting surgeons, and for the people that use the devices. And so we have a really great way that we can identify that this need should be impacted, and hopefully that will be one of the focuses of our project. Next slide. So ultimately, then we asked people at the end, do you have any other comments for us in the survey that go beyond the other questions? And people emphasize exactly what I said in terms of opportunities. It's a big and underexplored issue as far as the clinical implication, although some people said, you know, it's a low priority, there are few threats. Well, those are people who don't perceive what we are going to be talking about today and where these potential areas are. And so there's a real interest, however, in covering the topic through medical professional education and through cooperation with device manufacturers so that we understand that there are real benefits to how we can make this work in terms of the entire ecosystem across the device, supporting patients and their safety. Finally, the last question here is that clinicians more and more are encountered with regulatory burdens, and whether if there are additional disclosure responsibilities or informed consent responsibilities or other things that come along with implanting a device, what that means to the burden to the clinician who should take that responsibility of making sure that that patient is well informed and educated and is truly consenting for the process. And this is a place where the cardiac implanted device and particularly the Cardiac Rhythm Society has led on this and is ahead of the neural implant world. They've created guidelines and recommendation white papers to suggest how informed consent about implanted devices should be undertaken for heart rhythm devices. And it certainly is a direction that can be looked for in terms of policy and going forward in these neuro devices as well. So there's a lot of opportunity to integrate this within the manufacturers, within policy, and within education, within our academic societies. And I think this is really the right opportunity time as we're seeing the cultural moment is changing on this as well. With that, I'll turn it back to you, Dr. Amos.
Thank you so much, Dr. Petersen. Dr. Goldman, we are ready for you. Let me know when to advance your slides.
All right, thank you very much. Yes, please go ahead. So we've just kicking off today's events and this panel, we've already talked about the fact that we have to take different perspectives. We're taking a patient's perspective, a clinician's perspective, the device manufacturer's perspective, and some of those things are going to come up in greater detail as we move forward. But really, we are saying that we're taking a system perspective, although we have to drill down deeply vertically into every different stakeholder and the impact on them. So what I'd like to offer in this very short presentation is a framework that we might be able to apply, since it seems to be happening whether we wish to apply it or not. The idea that, especially when we're looking at brain-computer interfaces as part of a system, for example, with a prosthetic limb, we are closing the loop on something. And therefore, there is a body of work that exists today related to physiologic closed-loop control systems. And so this is a initial foray into examining how this might apply to the work we're doing, and maybe it could help inform what we're doing and help ensure we don't miss any of the corners of this area. So let's look at the implications for neuro cybersecurity on the next slide. So this is the only slide that looks like you're reading a standards document, because you are, sort of. And this is just to provide everyone with a reference point. So in the upper right corner, you can see the cover of an international standard, which is a number, it rolls right off the tongue, IEC 60601-1-10. There's actually a 1 missing in the enlarged part, but the upper corner is correct, -1-10. So this is a standard that's existed for a while, which is currently, as we speak, being actively updated this year, and that's relevant. Now, when you read the standard, you don't see the blue circles, but you would see this figure. And for those of you used to closed loop systems and these type of engineering diagrams, this is old hat. For those who aren't, it really doesn't say a whole lot that's useful. So we're just going to look at a few key parts. So the definition's on the right. A physiologic closed loop controller is a closed loop controller. We all are familiar with closed loop control. Our thermostats at home are closed loop control, but they're not physiologic closed loop control because in a physiologic closed loop control system, there is a physiologic variable that's being adjusted. So it has something to do with the body, something is being adjusted. And we're either trying to maintain something or set something. You might want to automatically control an infusion of something to control the blood pressure, for example. That would be physiologic closed loop control. So when we think about some of the key elements of that, again, they are circled in blue. In top, it's or a box. PCLC is the physiologic closed loop controller. And then Y on the right is the physiologic variable that's being affected, and you can see and measured. And I won't go too far into the details because we don't want to hear it. But in the bottom right is the formal definition. There's the physiologic variable, quantity or condition from a patient whose value is subject to change and can usually be measured. Usually be measured means sometimes it can't be measured, so you might use a proxy for that. That's important. It could be body chemistry, physical property, electrophysiologic, for example, and so on. So there is a construct and there is an international standard that is currently widely applied, especially in systems that are using, for example, exoskeletons already with BCI. So this is moving quickly. So this is a little bit of the foundation. And for those of you who are interested in this or want to understand where it comes from, this is really the source document. And as I mentioned, a new edition is being developed this year, and it will include BCI. And that's why I'm raising this here and now. So the next slide moves us a step away from that and starts to map this out to two things. Number one, in the upper left, you can see that there is an FDA guidance for physiologic closed loop control systems. And that guidance depends directly on the standard that we talked about, 60601-1-10. So they lean on each other, closely related, and therefore the update to the standard to include BCIs this year was actually taken at the behest of some of the technical experts at the FDA. So you can see the cross-fertilization that's occurring in this field. Now, the analysis in the slide, this of course is a ChatGPT drawn figure. So, take it as you may. On a number of iterations, it came up with some interesting ideas. So let's not hold ourselves too closely to it, but it was useful. But the idea, of course, is that you're measuring something from the patient, and in this case, you could be measuring whatever, motor cortex firing patterns, something that's processed. There's a range of possibilities that one measures, and then you interprets that signal and then is acting on that to move, in this case, a prosthetic limb. So how one maps the different parts of this system to the standard is actually, I would say, under analysis, because you can map things more than one way depending upon how the system will function. But the mapping becomes vitally important. So in any event, it is a system, and there are places in the system where information is transferred and places where failures can occur and where it's paramount to design well and implement well and look at every foreseeable problem to ensure safety. In the next slide, we jump into a few specific parts of the system in which one could corrupt key elements and inject, I'll say, trouble into a system. And so on the left, first of all, these are inherently complex. There are emergent behaviors that no matter how well one designs, these are going to be discovered. And even if there's nothing nefarious taking place. So inherently, we're dealing with something new and complex. And therefore, it's even more complex when something occurs to understand whether it's a system failure, design failure, component failure, or it's actually due to cybersecurity related activity. So on the left, we looked at a few examples of where model poisoning could affect computational elements, where their firmware exploit could affect the system, where one can manipulate a variable and have the prosthetic limb, for example, do things that were not intended. And any of these things would potentially or likely destabilize the system. And the impact of that, well, that has to be determined. And so this is just an example to stimulate thinking of that we should look at this as a system. This is being done. The standards are relevant and applicable as are FDA guidance. And this is a field that we will all be digging deeply into together so that we can assure it moves forward as usefully, safely, and effectively as possible, because it is transformational. And I think that's it. My last slide. Thank you.
Thank you so much, Dr. Goldman. Now we're going to now work our way towards Professor Burleson. Please let me know when to advance your slide.
I think you're just still on mute, Dr. Burleson.
How does that sound? Better?
I can hear you.
Is that okay? Are you hearing me?
Yes.
Should be unmuted.
One person is the speaker.
I know, that's why I was trying to get.
My speaker's off, my mic's on. Should be,
I can hear you, Dr. Burleson.
but I think Erika's showing.
She's talking to you. You need your speakers on.
Okay,
Good now.
all right,
Okay.
okay.
All right.
Okay, so thanks. I'm Wayne Burleson. I'm from UMass Amherst. We have a team that's spread across Northeastern and also a partner in Japan, Professor Sujawara. And what we look at is both analysis of vulnerabilities in existing systems, but also planning for future systems. I've been working in this area for probably 20 years. Wrote a book on it, and Kevin and I have collaborated in many ways, and Professor Sujawara has as well. And we design chips. We analyze different types of vulnerabilities. Let me go to the next slide, if you would. So we look at quite a variety from electromagnetic interference, side channel leakage, both active and passive. These are all areas that have been developed for other types of devices, and now we're applying them to the specific problems related to neuro stimulation and neuro devices. Wireless communication, the fact that can be jammed, it can be eavesdropped, as Dr. Petersen talked about earlier. The whole issue related to power, how are these devices powered? They rely on wireless powering. There's a number of problems that can come up with that. Over-the-air updates, software updates are required in most of these devices, both security updates and feature updates, making sure that is secure, can't be tampered with, man-in-the-middle type of attacks that would insert malware or something like that into the firmware. And also related to the AI aspects and the closed loop systems that Julian was talking about. So there are a lot of interesting problems in terms of vulnerabilities. And part of what's interesting to me about this, and I think the rest of the team, is that neural implants generate a lot more data than a lot of other medical devices because it's electrical as opposed to biochemical. So we have more data storage, data processing, uses of AI, and vulnerabilities associated with larger amounts of data. Control loops introduce all kinds of potential concerns, as Julian alluded to, and data privacy. And as Erika mentioned, I think this is somewhat of a new field, and that's part of why the National Science Foundation has given us this big chunk of money for a 5-year project to look at this. You can go to the next slide. So this is again a AI generated photo, in this case image of a closed loop mechanism that looks at brain neural activity and then has machine learning models. Those models may actually be very valuable to the device manufacturer, so they need to be protected from malicious modification, but also to protect intellectual property and counterfeiting of devices. And that's tricky because they're large models and they're in use. So protecting them from adversaries and eavesdropping is tricky. Go ahead, next slide. We also are concerned with the fact that there are many different parties potentially involved in these devices. You see on the right, there's the doctor, the nurse, the patient, the caregiver. All of these people have the potential to have malintent. and weaknesses of different types, and yet they need to cooperate, and they can cooperate in defending the device as well. So there's a area called multi-party computation, multi-party security that can be used to develop solutions for that. And last slide. We also wanted to look at the issue of troubleshooting. When something does go wrong with one of these devices, how do you deal with it? We talked about a fail-safe mode, but how do we do repairs? How do we maintain devices in the field? How do we update devices? How do we discard devices safely? Okay, one more slide. So this is just a summary of some of the vulnerabilities that we're looking at. Large categories, multiple devices, where devices may be sharing data. Potentially one device has been compromised. How do we protect that compromise from spreading to other devices? And then we're electrical and computer engineers. We're trying to design verifiable hardware and software that can be used to provide these capabilities. And I think my last one more slide. This is kind of technical. We're looking at the RISC-V architecture, which is an open architecture, which is generally a good principle in security, is to use open things as opposed to ARM or x86, which would be the other types. And we're putting in specific processors to deal with cryptography and machine learning and signal processing, and then designing this using modern principles of enclaves and techniques at the architectural and software levels for maintaining security, while also being very efficient with power. And so we're actually designing a custom chip that could be used as a platform for other devices. All right, thank you.
All right, thank you so much for that presentation. Now we'd like to have some interaction with all of our attendees. So I have created a Padlet, which is an interactive web-based tool. You can scan the QR, or you can type that tiny URL with go.illinois.edu/neurosecure into a browser, and it should take you to a site called Padlet, which has little tiles where you can add comments. So we have pre-seeded some questions that we'd like to get the community's input on. After all, our project is about community engagement, bringing together thought leaders to focus on neural devices. And so what we'd like to do is offer you a few moments to interact with the Padlet board, put some of your thoughts in there. And then while you're doing that, we'll look at the Q&A that was submitted while we were talking, and then we'll have an open discussion for the panel. So please take a few moments and navigate over to the Padlet. All right. Thank you all so much for interacting with the Padlet. We've been watching some of those comments come in. But I also see there's some questions in the Q&A tool on Zoom. And so I'd like to ask those questions to our panelists. So I'll kind of moderate here. The first question is, how do you describe the values and risks to patients when in most cases the patients are not knowledgeable nor understand AI, cybersecurity, and changes that are needed in going on or approved security, privacy, or safe and effective use? Erika, could you provide some insights into that?
Yeah, this is really complicated because, as I said in our survey, a lot of clinicians don't, I think, have a knowledgeable or familiarity with that as well. And this is something where we need to make sure that a couple of things happen. One is that the clinicians need to be conversationally familiar with some of the risks, not just of you might have bleeding or infection from a surgery, but once you have a device, these are other risks that come down the line with it. And so as we start to incorporate these new technologies, we need to be able to expand on discussing those. But that means we have to provide and equip clinicians with that vocabulary. And so the American Society of Pain and Neurosciences, from which I'm the past president, just published a clinical expert opinion guideline this past quarter to talk about guidelines for the use of AI in clinical practice in pain medicine. And so the idea there is to try to reach out and provide some expert guidance to the clinicians to start helping to create some of that floor of fundamental essential information. Once you have that, then I think it's important that there also is a responsibility from the manufacturers to ensure that clinicians who are implanting these devices and are using them have the familiarity and can describe some of those issues as well. There is a potential legal exposure to those manufacturers, and it is in the best interest of the manufacturer to ensure that they're using clinicians have the familiarity that also then ultimately shields that company from that legal exposure as well. And so part of that then comes down to, can we as figure out the best ways to communicate this simply and easily? The FDA has a role in this as well. They've developed some videos that are just out on YouTube that are there to introduce issues in cybersecurity, and anybody can go view those videos. And it's something that, again, a community member who is hopefully going to have advocacy and agency about their own body and their own device should be able to access and get some of this information. So kind of we need to develop a Swiss cheese approach to this. We need to make sure that this is coming from multiple levels in the process, but ultimately I will always have a patient who says, you're the doctor, you pick what's best for me. And I can do my best in that sense to say, okay, I am doing my best, doing what I can to communicate to you, but I don't want to be paternalistic on something that is in your own body where you are the patient with agency and autonomy. But we need to recognize and then ultimately document that all of these approaches have been taken. And then if a person chooses not to drink the water, you at least led the horse to the water. And so I think that we can figure out how to build a good block of Swiss cheese in order to try to make sure that all that information gets there. And hopefully some of it comes through.
Thank you so much, Dr. Petersen. I also appreciate a lot of your analogies to make this a little more accessible to all of us. Dr. Goldman, I think we have a question I can direct to you. Neuromodulation devices interface directly with the nervous system, meaning a cybersecurity compromise can translate into an immediate psychological or physiological effect. How do you view the potential harm of security incidents in neuromodulation compared to other medical device classes, and what safeguards should be considered essential?
That's a very good question. And it sounds like it's a unique problem, a new problem. I mean, it is new in some ways. Technology is new, and we're still learning about the impact that may occur. But there are and have been problems with insulin delivery systems, for example, and the effect of that is really, maybe not as immediate, but it's pretty immediate and quite devastating, and the consequences can be very severe. Imagine, a person with diabetes is driving, for example, and they're driving a bunch of people in their car. So let's not underestimate, how well I think society and manufacturers and regulators and the community has done to kind of move that whole field forward with diabetes management. It's been really quite a success story, although with fits and starts with technology. And also there are and have been security issues there. It's really and there are similar challenges. Patients don't necessarily understand the inner workings of their insulin delivery system and their glucose management system. Of course, some are part of the hacking community. Some of them are part of the Diabetes Technology Society and group, and they've really advanced the field, that leading edge. And the same with clinicians. And when there have been security issues, the manufacturer makes a recommendation, but then really, there's a scramble, clinic scramble and the physician scramble. Everyone scrambles to figure out what should they tell the patients, how do they disseminate the message. The information is hard for them to understand. They call the clinics, they call their physicians and offices, and they don't know what to do. So we do see the chaos. We see some of the confusion. We see this at institutions. There are physicians who receive these notices who don't manage the patients or don't have access to the devices. A lot of confusion. I think the short version is we can learn from the success stories and the struggles that we're having in these other fields, whether they're in rhythm management, cardiac rhythm management, or diabetes, for example. We should build on those. We should investigate those, and therefore make what we do in this field as painless as possible and be as effective as we can to address these issues.
Thank you so much. I wanted to pull actually a question or comment from the Padlet next, and this will go to Professor Burleson. So one more second. Sorry. So the biggest unsolved problem is not smarter algorithms. It's making the systems work safely and reliably. Signal drifts, tissue changes, batteries and heat are unforgiving, and updates have to be secure. So what would you say is like a holy grail for long-term stability? You can unmute.
That's a big question. That's I think the whole research project and summarized. I think somebody mentioned it in a related question, something about zero trust architecture. I don't think this is really a zero trust architecture, but it raises an important point of who has control. And we're probably going to see cases where there's a lot of re-authentication, multi-factor authentication, like you see now when you use devices, because many of the rudimentary authentication techniques, basically, that allow somebody to take control of a device, whether it's the patient or a caregiver, those are vulnerabilities. So that's an important issue. Many of the defense tech, the modeling, the threat modeling and defenses can be drawn from other fields. So it's not like we're reinventing everything here. So for example, powering wireless communication, we have pretty solid solutions for a lot of that, encryption, re-authentication, things like that. But you raise the point that there's a lot of different issues, and that's part of what makes security hard. Many of them we want to hide from the user, and that's part of why we're providing more computational power on the device. But there's always a risk when you make the device more complicated that you introduce new vulnerabilities. So it's going to be a challenging problem. Thank you.
All right, thank you so much for that. We probably have time for just one more, and there's a few to choose from. I guess I'll take this one. So from a clinical governance perspective, I'm interested in how secondary biomarkers are handled if an implantable system passively captures data that's indicative of suicidal ideation. Who bears the ethical and clinical responsibility for patient outreach, safety intervention, and determining next steps? So Dr. Petersen or Dr. Goldman, would you like to take that question?
It's a great question for Dr. Petersen.
Yeah. Well, I don't think it's currently possible. What we see is if a device stops working, the most dramatic example of that right now in clinical commercially available practice is with a deep brain stimulator for Parkinson's. Occasionally these patients don't recognize that their battery is approaching its end of service life, and all of a sudden they wake up one morning and the device isn't working anymore, and they are completely locked up with severe Parkinson's because the device is no longer providing its therapeutic benefit. So it has stopped working and they are stuck. And so that is sort of the level and extent of how hazardous that can be to a patient. And it can be a medical emergency for that patient, but not necessarily in a denial of thought kind of attack. One of the concerns that comes with brain-computer interfaces, though, particularly in systems that are interconnected, as you saw from Dr. Goldman's slides, and thinking about Dr. Burleson, what happens within the Internet of Medical Things as these devices become connected and not just closed systems, then you do worry about, is there something that could happen if you have and some sort of a anomalous signal or a rogue pathway within that causes the system to seize up, lock up, or cause some sort of difficulty. I'm thankful right now that I think that still stays in the science fiction side of things, but it doesn't mean that if we're asking that question, that somebody with a potentially malicious intent isn't also trying to think of that question as well, which is why we need to be ahead of it.
Thank you so much for that response. Actually, a question that just came in was about the NSF research and when it will kick off. It has kicked off. We received the funding in the fall and started kind of getting together as a group. So I expect that you'll see a lot more from us. I'm certainly excited to get more patient information and clinician information. We'll also be reaching out to manufacturers and getting their input so that we can pass it along to the technical research team and also the clinical like education components that we're hoping to put out from this project. So you can learn more, and we can put the link in chat again to learn more about this NeuroSecure project. But we really thank you for your time and interaction. We'll be using some of the comments that came from the Padlet and also the questions that you've posed today to kind of help inform our work. And so we really do appreciate all of your engagement this morning. We will take a brief pause as we transition between speakers. So please don't go anywhere, but you will see the screen turn off, and then I'll pass back over to Kevin.